These are some of my favorite math stories. In this episode, Mathematics is the Chaos Game. We'll explore a class of fractals generated by the Chaos Game, or iterated function systems if you want a fancier name for it, that elegantly solves an important problem in computer graphics. The Chaos Game comes from Michael Barnsley, who turned it into an industry in the 1990s. In its original form, you start with 3 points, A, B, and C. I usually place them as vertices of an equilateral triangle. Pick a starting point at random, say A, and mark that as your current point. Then repeat the following process. Pick A, B, or C at random. Move halfway from your current point to the randomly chosen point, and mark that as your new current point. So, say I start at A, and then randomly choose B. Mark the point halfway from A to B. Suppose I choose A next. Go halfway from the current point to A, and mark that. If C is chosen next, move halfway to C and mark that point, and continue for as long as you can stand. What pattern will your dots form? Most people suspect the triangle will get filled in completely. The actual answer is surprising and beautiful. The result is a sizable portion of a fractal known as the Sierpinski triangle. Amazingly, we see that in the episode on Pascal's triangle. To form the Sierpinski triangle, start with the triangle. Let's make it equilateral again. Mark the midpoints of each side of the triangle. Connect the midpoints with segments to form an interior, upside-down triangle. And remove all of those points inside of the interior triangle. What remains is bordered by 3 triangles. Repeat the procedure on each of the 3 triangles. Connect the midpoints and remove the interior triangles. You now have 4 holes, and the remainder is bounded by 9 triangles. Repeat the procedure on each of the 9, and continue that process. What is left after doing an infinity of removals? Well, the answer is crazy. On the one hand, all area has been removed from the original solid triangle. On the other hand, you have line segment borders that have infinite length. What's left looks like nothing and everything at the same time. These conflicting properties gave mathematicians a challenge in the early 1900s. The Sierpinski triangle and similar geometric constructions are now called fractals, and they're very different from standard geometric figures. For this episode, we want to focus on why the Chaos Game reliably produces the Sierpinski triangle in spite of its random nature. First, notice that the triangle includes miniature copies of itself. At the top, lower left, lower right, and on to infinity. So here are the 3 rules of the Chaos Game. Move halfway to point A, halfway to point B, halfway to point C. Let's apply each rule to the entire Sierpinski triangle. If A is at the top, moving all points in the triangle halfway to A results in the smaller copy of the triangle at the top, shown in green. If B is lower left, moving all points halfway to B results in the smaller copy of the triangle in the lower left, shown in purple. If C is lower right, moving all points halfway to C results in the smaller copy of the triangle in the lower right, shown in blue. The entire triangle is composed of the union of the 3 disjoint smaller copies produced by the rules. Barnsley generalized this result as the collage theorem. If you have a geometric figure G that can be broken into components, with each component the result of applying a rule, a contraction mapping to be precise, to G, then G can be approximated by applying the rules sequentially to points or sets of points. Well, that's a mouthful. Here's an example. Suppose we want to generate a digital fern leaf. Instead of storing the locations of all of the pixels needed for this graphic, the collage theorem suggests finding miniature copies of the leaf that add up to the full leaf. One miniature copy is the lowest branch on the left. Shrink the full leaf, rotate it a little, and move it into place, all of which can be accomplished very simply mathematically. A second copy is the lowest branch on the right. Now, we could keep going 1 leaf at a time, but there's a more efficient way. A third copy is the leaf with those bottom 2 branches removed. As it turns out, the Chaos Game using those 3 rules produces a very nice looking fern leaf that is missing its stem. So a 4th rule is needed: squash the leaf into the stem. Why would these 4 rules be useful? Well, it only takes 6 numbers to describe such a rule mathematically. A 2x2 matrix plus a 2-dimensional vector. This is way less storage than saving the locations of each pixel. Plus, the rules generate infinite detail, allowing you to zoom in on a region of the fern and maintain a good resolution. In some ways, this is the ideal for computer graphics. Very little storage required, and the ability to fly around and zoom in and out of the image. As CGI plays increasingly important roles in video, these are important tools that have been adapted to good use. In case you're wondering how flexible the technique is, after all, most images don't have the obvious embedded copies that the Sierpinski triangle and the fern do. Here are some images that Barnsley created using 32 rules or less, as shown in the book Fractals Everywhere. And yes, the cover is one of the images. Now you can probably find 3 rules that generate the maple leaf. But notice how sharp the zoom in on the smokestack is, and how realistic the smoke is. The detail is essentially infinite for little cost. Amazing.